All right, recording is rolling. Today is Monday, October 17th. You guys know we've been doing a few topics put together. We've got universal gravitation, which is this right here. We've also got like centripetal force, and which this was one of the labs you guys did recently. Right? And we're putting those ideas together to get orbital mechanics. Right? So like those type of stuff. All right, so we're doing all this. Oh, here's scaling. That might help us out later too. Okay. So main thing we're focusing on today is you guys got this page I gave you guys a while back. It's got conceptual questions related to universal gravitation. A lot of these questions are going to show up on your guys' next quiz, so we'll cover these in a Kahoot today. You guys got your phones out, turned on, connected to the internet. Okay. Now, before we hit the Kahoot, though, I've got a few other demos lined up for you guys first. So let me switch my screen and let's go on an adventure through space. We're going to go to, let's say we're zooming through space and we come across this really weird planet that is completely hollow. And where's Paul Hewitt? Here it is. All right, Paul Hewitt.
Any object in the center would have no gravity because it'd be pulled in all directions equally. Do we see that?
Actually, you know, what you said right there is an important point that it takes some students a while to get onto here. But guys, suppose you did dig a tunnel all the way to the center of the planet, right? Now let's ignore the fact that it's all molten and the whole deal, right? Let's just think about the gravitational effects. Suppose there was like a cave right at the center of the planet, right? Guys, would you be very heavy or completely weightless right at the center? Guys, how about this, guys? Which way would be down right at the center? Could you like stand on the floor? Or how about this? Do you think every single grain of sand on the planet would be pulling you a different direction? And if all the forces are pulling you a different direction, do all the forces balance out? Right? Do you think you'd be floating around like an astronaut? I think you'd be floating around like an astronaut right at the center of the planet. Right? Okay, so let's take this cave and just make it ridiculously big so that we actually have like an eggshell planet. Okay, so you guys see this eggshell planet? All right, so back to here.
Because it'd be pulled in all directions equally. Do we see that? But what I want to do is I want to convince you that it would cancel out no matter where you are. And so what we'll do is we'll take a point that's about here, where this distance here is twice this distance. Do you think it would still cancel out this side and this side? What we'll do is we'll consider a solid cone of material. We'll call this M1. We'll call that D1. We'll call this M2 and 2D. Well, just D and 2D. Let's look at our equation. Let's have the equation guide our thinking, gang. The force over here would be our mass, say the mass of the point, okay, times M1 divided by D squared. That's this force. The force that's pulling over here, you might think it's more because there's more mass. Or you might think it's weaker because it's further away. And guess what one does to the other? Okay. When you're out here, it'd be twice as much this way, but twice as much this way. So how big would M2 be compared to M1? You see it's 4? It's 4. So M2 would be 4 times M1. That'd be like 4 M1s, boom, times your mass, MP, divided by this distance here, 2D squared. But when I take the twice the distance and I square it, what do I get, gang? Isn't it like 4D squared? And what do the 4's do? And what's this? The same darn thing I got here. So you know what? The pull here, equal. I just took a place that was easy because I got twice the distance here as here. But you put any distance you want and that will happen. Anywhere inside there, there'll be no gravity. There'll be no field region. Inside a shell like that, there'd be gravity-free region. There'd be no gravitational field due to this mass. It would cancel out everywhere.
Oh, yeah, so pretty cool, right? All right, so we're zooming through space, we come across this eggshell planet. You can walk around on the surface of the eggshell planet, no problem. Right now, it might be kind of small force, but be there. Right? But as soon as you step inside, ooh, gravity-free zone. Okay. I want to take that and extend this a bit. Okay, so let's go back to a regular solid planet. Okay, so we've got a regular solid planet. Okay. And let's go on a journey to the center of this planet. So here's this guy with a shovel. He's going to dig a spiral staircase down the center. Now, you guys know right at the center, suppose there's like a cave in the center. Okay. You guys know that this would be, well, all the forces would pull you a different direction. They would all cancel out. Okay. Where's mine? There it is. Okay. It's pink ink. Okay. So right at the surface, the guy has one gravity force just pulling down. But right at the center, okay, it's got force, 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 force. Everything cancels out. Okay. Oh, you know what else I know? I know if you take off on a rocket. So here's a rocket. This guy's taking off. Okay. The further you get from the planet, there's less and less gravity force. In fact, that's going to follow an inverse square law, wouldn't it? We go force equals g m divided by some general distance squared. Okay. The big M is the mass of the planet. The little m is the mass of the person. And then this r, well, to go from here to here, be some generic distance, lowercase r. Okay. And if you like to assert this, I'll call it capital R. Right, that fixed distances. Okay, so we got this. Okay, let's put this all together in a graph though. Okay, and the axis I want to do on this graph is I want to know what is your weight. Now your weight, that's what this force is, right? It's like your weight. Okay? As a function of how far you are, your radial distance from the center of the planet. Okay. So your weight can be measured in newtons, your distance from the center could be measured in meters. Okay. And all of us have spent our entire lives right here at the surface, which is this fixed radial distance, capital R, from the center. Okay. So I'm going to put that very special location on this graph. I'll call this capital R right here. Okay. Okay. So there's 2 points I know for sure I can put on this graph. I know right at the surface, I can definitely put my weight. So it's like right there, like mg, whatever that is. Right? So that point says all of us have only ever experienced that point our entire lives. Okay? And we thought about this a little bit. So, hey, right at the center, we know that there would be, so at 0 from the center, 0 meters, you have 0 weight. So that point must also exist, right? So we got those 2 points. Okay. I know if I take off in a rocket, there's an inverse square relationship between the gravity force and the distance. Okay. Can you guys graph like y equals 1 over x squared? Because that's a lot like this would look like everything beyond this capital R. Okay. Wouldn't this go out like this? Isn't that what they'll look like? It's like slopes down like that. Okay. There's a horizontal asymptote here at 0 newtons, like 0 newtons. So if you're crazy far away, it's going to just approach 0 newtons from the Earth. Okay. But what about the rest of this graph? What about as you're tunneling down the spiral staircase, which is somewhere between here and here? What's that going to look like? Okay. Like, what if you're halfway down the spiral staircase? Like this guy right here is halfway down to the center. Okay. How many guys think that if you're halfway to the center, you have half the weight you do at the surface? Like half and half, you guys think? Okay. Which should be like right, bam, right there. Okay. Another way to say that is that there would be a linear relationship between the center and which your weight is, right? So it would increase that linear rate, okay, of course, until you get to the surface. Okay. Now, how can you prove that? Well, this goes hand in hand with that eggshell planet you guys saw with Paul Hewitt, because suppose this guy at the center, okay, isn't it like everything above him in elevation is like a series of eggshells? And Paul Hewitt just sort of proved to you guys that all that's going to cancel out. So everything above this guy in elevation is like a series of eggshells that just cancels out. So all the gravity acting on this guy is really what's just below him in an elevation, which is just this bit right here. It's almost like a tinier planet, right? And the radial size of the planet is going to, the mass is proportional to the volume of the planet, which scales up as a factor of radius cubed, right? Isn't volume something like radius cubed, right? Like if it was a box, it would just be base times width times height. The fact that it's a sphere, it's the same principle in terms of scaling. So this is like proportional to radius cubed. Okay. And this force is also inversely proportional to the radius squared. So guys, what's radius cubed divided by radius squared? R cubed over R squared. Force is proportional to Isn't that just r? Right. And that's why this is a straight line, basically. Right. You guys get that? Right. Next concept. Well, let's talk about tides a little bit. Talk about tides. Okay. So, because the Earth, is the moon pulling on the Earth? Yeah. Is the sun pulling on the Earth? Yeah. Right. So the moon's pulling on the Earth. The sun's pulling on the Earth. Right. Now, guys, what's the main driver of the tides? The moon or the sun? The moon, right? Now, does the sun also have a tidal effect? Yeah, it's just a lot smaller, right? So the moon is the main driver of the tide. Hey, what about gravity force? What if we took this F equals gmm over r squared? Right? Guys, here's the mass of the sun, mass of the moon, mass of the Earth. Here's the universal gravity constant. Here's the distance from the Earth to the sun and distance from the Earth to the moon. Suppose we pumped numbers into this expression. What force do you think is bigger, from the sun to the Earth or from the sun to the moon? Or sorry, from the sun to the Earth or from the moon to the Earth? That's what I meant to say. Okay. Let me see, show of hands. How many guys think that the force on the Earth is greater from the sun? The force on the Earth, talking about gravity force, right? Gravity force is greater from the sun. Okay, got some votes there. How many guys think that the gravity force is greater from the moon? Who thinks that? Okay. All right, let's do a practice run here. All right, so I'm just gonna take this number, pop it right here. So here's my 6.67 times 10 to the power negative 11. Multiply by the mass of, let's start going sun to Earth. How about that? So this could be the sun, this could be the Earth. So the sun is 1.99 times 10 to the power 30. The Earth is 5.97 times 10 to the power 24. Okay. Then divide by the distance from the Earth to the sun is 149 billion meters, and don't forget to also square that. Okay, that comes out to 3.57 times 10 to the 22 newtons. That would be newtons, right? Okay. Now, if you do the same math between the Earth and the moon, here's what the answers end up being. Okay, so from the sun to the Earth, it's this number. From the moon to the Earth, it's this number, right? And which force is bigger? Well, the most important thing to look at to answer that question is the power of 10, isn't it? Right? Guys, 10 to the 22 versus 10 to the 20. Okay, so what's the answer to the question? Which force is bigger? From the sun or from the moon? The sun, right? It's not even close. It's like over 100 times. Because 10 to the 22 compared to 10 to the 20, that's a factor of 100, right? Okay, and 3 is bigger than 2. So yeah, so it's over 100 times more. Hold on a minute. If the force from the sun is over 100 times force from the moon, then why is the moon the main driver of the tides? And it has to do with the proportional distance from the close side to the far side of the Earth from each of those objects. Right. So let's start with the moon because that's the answer to the tides. What causes the greater effect? Right. So the fact that the Earth has a diameter. Right? See, like all this force goes gmm over r squared. We've been assuming like center to center, right? Center to center distance. But you could get more specific and say, well, there's a close side and a far side from the moon, right, on the Earth, right? And if you take the proportion, right, what is that distance proportionally? And you can compare that to proportionally from the sun. See, the sun is so far away that from the close side to the far side, right, that proportion is almost a 1-to-1 ratio, right? Not exactly, but a lot closer to 1-to-1 than it is from the moon, right? Guess that. And so that's related to tides. It has to do with those proportional distances, right? Right. Two more things, and then we'll start the Kahoot. Okay. Oh, could you guys imagine? I mean, this is gonna come up. This is gonna be one of the Kahoot questions. Okay. Here, let's put different objects in orbit around the Earth. So here's the Earth axis. I'll do it right. Okay. Let's start with low Earth orbit. Okay, this low Earth orbit is probably pretty close to what I just drew right there. Okay. Here's the International Space Station. Okay, going around. Do you guys know how long it takes the International Space Station to go around the Earth? Okay. Like, if you guys know orbital speed around the Earth, low Earth orbit, it's about 8,000 meters per second. Okay. I think 7,900 we calculated the other day, something like that. Let's call it about 8,000 meters per second. If you know the circumference of the Earth, so that's a distance around, you know the speed, put 2 and 2 together, you can calculate the time. Does anybody know how much time it takes to go around the Earth in orbit? It's about 90 minutes. About 90 minutes. So the astronauts on the International Space Station, about every 90 minutes takes them to orbit. Right? Now, out here at the moon, here's the moon, like way the heck out there, right? Takes the moon how much time to go around the Earth? 1 month, right? Same root word, moon, month, same root word, right? Ah, okay. So looks like the further out you are, the more time it takes to go around. Right? In fact, Kepler would have loved this question because Kepler nailed down that relationship um, like this, right? So the further you are out, the more time it takes to go around. This is the proportionally the relationship, right? Guys remember that? Kepler's third law. Okay. All right. So do you think that there's a place, probably right about here, that you could park a satellite and it would take 24 hours exactly to go around? Can you guys imagine that? 24 hours to go around? Okay. And what would that look like from the point of view of Earth? If you look up in the sky and see that satellite, what would it look like the satellite's doing all day? Just staying right above head, right above, wouldn't it look like? Right. That is called a geosynchronous orbit, right? Geosynchronous, like synced to the rotation of the Earth. Okay. So that's a concept that might pop up as a question. Okay. And one more thing before we hit the Kahoot. I've got a cool demo for you guys. Okay. So Lagrangian points. I want to teach you guys about Lagrangian points. So do you guys think that between the Earth and the Sun, for example, there's some point where the gravity cancels out? Right? Like the Sun pulls to the left, the Earth pulls to the right, and it's a wash. Right? There probably is, right? Now, I don't think that point's very stable. Right? It's kind of like trying to park a baseball on top of a mountain, right? It's going to roll off one way or the other, right? But it does cancel out, right? Now, is that geometrically halfway between? Like if you were geometrically halfway between the Sun and the Earth, you would obviously follow which way? Towards the Sun, right? Because the Sun's way more massive, right? But there's some point that's closer to the Earth, right? Okay, you guys get that here, right? Okay. Now, in a static solar system, that would be the only point where things could possibly cancel out. But the fact that there's also orbiting mechanics, right? There's this dynamic situation set up. Let's look at this point that says L2. So from the point of view of L2, aren't the Sun and the Earth both pulling you to the left, right? So there's definitely a net force on you, right? But the fact that the Earth is also going around the Sun at the same time, do you think you could sort of have your own orbital radius here, where you were like tracking along the Earth? Sort of like that geosynchronous satellite example I was just telling you guys about. So sort of like that, right? Right, just kind of hovering. In fact, you guys remember James Webb Telescope was launched less than a year ago, right? It's been sending back a bunch of really cool pictures, right? That satellite is actually in orbit about the L2 point, okay, as it's going around. Okay. So a bit more stable there. Think about it a little bit. If an L2 exists, there must also be an L3 by some symmetry. Now L3 is the least stable of all the points, so it's like Jupiter like flies by, causes a perturbation, and can throw everything out of whack. But there is also an L3. Right? In fact, people used to speculate there might be a planet out there. Now nowadays we know there isn't because we have space probes. We look there, there's nothing there. But it used to be an idea. It was a popular idea at one point. Okay. Now, along comes a guy named Lagrange, who these points are actually named after. He does a bunch of fancy math and realizes, oh, hey, there's actually 2 more points of gravitational stability. You can make these, I guess you have like a perfect right triangle right here. Perfect right triangle. Right. So L4 and L5. Right? So pick 2 points. One's orbiting the other. Right? You get these L4 and L5. And L4 and L5 are actually the most stable gravitational or Lagrangian points. And I can show that to you guys. Right. So here's an animation of our solar system. The Sun's right at the center. And so here's the Sun at the center. Here's Jupiter going around. You guys see Jupiter going around? Okay. Hey, do you guys see a bunch of pink dots? What do you guys think those pink dots are? Those are asteroids. That's the asteroid belt. The pink dots are the asteroid belt. Right? In fact, we're kind of lucky to have a big old mass like Jupiter as one of the planets in our solar system because, see, it's sort of protecting the inner planets from all those asteroids. Right? Yeah, Jupiter is, right? Pink dots are the asteroid belt. But do you guys see 2 green patches of dots? Oh, wait, back up. Okay. Back to the pink dots, the asteroid belt. See how the asteroid belt looks kind of triangular-ish, right? Do you guys see it? This right here would be the L3 point between Jupiter and the Sun. It's on the opposite side of Jupiter. You guys see that? Okay, so that's kind of interesting, right? All right, so now those green patches, those are called the Trojans and the Greek asteroids, and those are at the L4 and L5 points between Jupiter and the Sun. So you guys see Jupiter, Sun, you can make like an equilateral triangle, and the third point of the equilateral triangle are those green patches. You guys see those? All right, so there you go. There's Lagrangian points.
Right, and if you ever want to park a satellite somewhere where it's out in deep space but kind of stable, not going to run into anything, if you pick two large masses and the L4 and L5 points, then those are usually pretty good places to park stuff. Right. All right, let's get going on Kahoot. All right, start this thing. Bring this over here. All right, you guys got your phones out, turned on, ready to go. Classic. All right, you guys got your multiple choice answers out. Follow along. Some of these are going to be quiz questions. You guys know that. All right, and let's get going. Newton hypothesized that the moon yeah, there you go. All statements are true. Right? It's gravitationally attractive, but also moving to the side at just the right speed to like fall around the Earth and therefore stay in orbit. All right, following around the curvature of the Earth. Look at all those points. Oh yeah. Question 2: if the mass of the Earth increased with no change in radius, the Earth becomes more massive. All right, yeah, there you go. All right, you would also become more massive. Right, so this is just GMM over R squared. Actually, here, I want to flip the screen because especially for the next question that's coming up. Right, so we are here. Right. So this is the formula that's going to navigate that question, also the one that you guys are about to see. Right? Except I'm going to modify the scenario a little bit. Instead of like just two objects floating around space, I'm going to turn this into a planet and a person, right? Just like that. Okay. Okay. So some distance r here. We got the force of gravity is universal constant times the mass of the planet times your mass divided by this distance squared. Right? Now the one you guys just did is well, if the mass of the Earth increases, you know, all these other variables the same, then your weight would also increase, right? Your weight would up. Right? Now the question you're about to get, right? It's up, so you guys can have an extra few seconds to think about this. Is what if you like pack this planet down, like crunched it down, okay? So that all the masses stay the same, everything in the numerator stays the same, but you are like crunching this down so that the radius is decreasing. Okay? Now the density would not stay the same, right? The density is going to go up. Okay? So everything in the numerator stays the same, and the denominator gets smaller, smaller, smaller because you're like packing it down. In that case, what's going to happen to your weight? That's the question you're about to see. Okay, so let's flip this back over. Okay, let's see if you guys can navigate that. All right, got Liam, Terry, Evan, David, and Cole. There you go. Nobody got that. All right, so flip back over and let's step through this. All right, so you're saying if the radius decreases with no change in the masses, right? Yeah, another way of saying this, like you're like packing the planet down, like squashing it, right? So this guy sees he's on a shrinking planet, but it's staying the same mass, right? It's just getting physically smaller, right? Well, let's run the numbers, right? Let's say, for example, some original force is like, let's say all the top stuff comes out to like 24 units. I don't know what, some units, right? And the denominator comes, so r squared comes out to like 8 units. Guys, what is 24 divided by 8? 3, right? And then force could be like measured in newtons or something, right? Okay, right. Then suppose you crunch this down, like crunch, right? So that all the stuff in the numerator stays the same because the masses aren't changing. So it's, if it was 24 units before, it's still 24 units, right? But if r is decreasing, well, the r squared is also getting smaller. So would that be like 6 units, for example? It could be like that. Okay. And then what? Guys, what's 24 divided by 6? Like 4? You guys see that as the radius and radius squared gets smaller, 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 that the your weight is actually increasing? Is that okay? Yeah, so you actually weigh more. Okay. The gravity force between two massive spheres. Yeah, those are all true statements, right? It's always an attraction, depends on each of the masses, and also inversely, right, so the force is inversely proportional to the square of the distance between them. Right? Inverse square relationship with distance. All right, carry to the top spot. Two objects move toward each other. As they get closer, what happens to the gravity force? Yeah, gravity force would increase. So swap back over here, show you guys why. Okay. So now we're looking at like this type model. Okay. Hey, suppose maybe it's like 2 asteroids, right? If these 2 asteroids are really far away from each other, wouldn't it be very tiny, tiny, tiny force? And as they get closer and closer together, isn't that force going to like, increase? Right? Which is the answer to the question. Right? But here's the formula to back this up. Right? So see each of the masses that didn't change. Right? This radial distance. Hey, this radial distance between the two gets smaller, smaller, smaller. Is that also going to increase the force? Okay. Which is the same math as sort of we just did, right? If you have a decreasing denominator, then the numerator overall blows up bigger, right? Right. There you go. So we back that up too. Whoops. Suppose gravity force is 100 newtons. If the distance is doubled, yeah, we're down to a quarter of the original force. This is because of the inverse square law. So if the original force is 100 newtons, a quarter of that is only 25 newtons. Here. Right. So, so we got this distance, right? And we're gonna double this distance, right? So if you throw a factor of 2 on this r, guys, what's the factor of 2 squared? That'd be 4, right? Yeah, maybe we should write this down on paper a bit differently. Right, so
Right, so we got force equals G-M-M over R squared. Okay. Suppose that was like 100 units divided by 1 square meter, right? So they come out to like 100 newtons, right? And now we're going to take this R and we're going to double it. So a factor of T squared is 4. So 2 squared is 4. Okay. So now we're down to 25. Okay. Like just like that. You know what question I think might be coming up real soon? Set you guys up for this. What if you have a planet? If it's not this next question, it's one of these down the line. Okay. You're standing at the radial distance from the center of the planet, of course, just like all of us ever have. Okay. Could you guys imagine if you're standing on top of a very tall ladder that was also one radius tall, one Earth radius tall? Okay. Because what would happen effectively to your distance from the planet? Guess you would be doubling that. Okay. And if your weight is of course a gravity force, which is like this, right? Here's your mass, here's the mass of the planet, right? Then if you double that distance, if you double this, double squared is 4, okay, divided by 4, right? Okay, so you have like a quarter of the force, right? Let's check this out. So inverse square relationship. If you double the distance, you get a quarter of the force. Carries on fire. And then get some points. The force of gravity on you is greatest when you are standing where? Yeah, on our surface. You guys remember we just talked about this before I started the Kahoot. I say if you like tunnel into the earth, right at the center you have 0 weight. At the surface you have whatever weight you usually have. Take off in a rocket, inverse square relationship, it decreases. But then going back to like tunneling down to the surface, there's a linear relationship. You guys remember talking about that? Okay. So right at the surface is where you would weigh the most. Surface weigh the most. Okay. Remember that? Lunar month, about 28 days. But what if the moon were closer to Earth than it is now? Yeah, less than 28 days. All right, all right. At an extreme, right, you guys know low Earth orbit takes about 90 minutes to go around, right? And then the further you go out, the more time it takes to go around. Right? So if the moon were closer, it'd be less than 28 days. Right? Kepler would have liked this question a lot because Kepler could have nailed down exactly the relationship with this third law of planetary motion. Right? How far and how much time. Here's the ladder question. So you weigh 400 newtons. Now you go to the top of a tall ladder. So you effectively double your distance from the center of the Earth. Now how much do you weigh? Okay. So, because if you double your distance, don't you have a quarter of the original force? And isn't a quarter of 400 just 100? Right? So this is the inverse square law relationship. Okay. Here, let me flip over so you guys can see this picture. Okay. So if you go from here to here, see how you're like doubling your distance from the center of the Earth? Right? Oh yeah. Yeah. Okay. So if you double this R, right? See like oh wait, did I write some math before? I don't know. Right, anyway. Okay. So suppose this comes out to like came out like 400 divided by 1 squared is equal to 400. And it's gonna be like newtons. Okay. The new force could be the same whatever units, crazy units these are. But if you double that r, 2 squared is like 4. So now we're down to 100 newtons. Right. Another way to see this graphically is you take this r, double this to 2r, which is like out here. Well, but this was exactly the scale. Should be like a quarter of the force right here. Right about there. There you go. There's the relationship. Okay. So double the distance. So you got a quarter of the force. Double the distance, a quarter of the force. Ah, Liam, on fire. Suppose the gravity force is 100 newtons if the distance gets cut in half. Ooh, cut in half. Yeah, you'd get 4 times the force. Okay. This question, if you're paying real close attention, is actually the exact reverse of the previous question. Let me point that out to you guys. I'm gonna flip the screen over. Okay. So the question before, I'm going back to the question, was if you're on the surface and you double your distance. Remember how you went from 400 newtons at the surface to only weighing 100 newtons way up here? You get a quarter of the force for double the distance. Okay. But the question you guys just did right now is like you climb down the ladder. So at the top of the ladder, you weigh 100 newtons. And if you climb down the ladder, haven't you effectively cut your distance to the earth in half, right? From 2r to just plain r. So now you have 4 times the force that restores your weight back to its original value of 400 newtons, right? Is that okay? Right. So inverse square law between distance and force, right? If you increase the distance, you get less force. If you decrease the distance, you get more force, and it follows an inverse square law. So 1/2 squared is a quarter. 1 divided by a quarter, 4 times. 4 times 100 is 400. According to Newton's laws, a rock and a pebble will fall with the same acceleration, true, in a gravity field. Why? There you go. Ratio of force to mass is the same, right? Now, what the red one says that they weigh the same. Well, that's not true, right? Every object will have its own individual mass, its own individual inertia, and its own individual weight. But if you take the ratio of weight to mass, see, isn't that what Newton's second law of motion is? Newton's second law of here, flip over. Doesn't Newton's second law of motion say force equals mass times acceleration? Acceleration is a force acting on a mass. In fact, if we're talking about weight, then isn't that what free fall gravity is? Different weights, different masses. The ratio is the same at the surface. Right? And the surface of Earth, that number is 9.8 meters per second squared. You guys remember that? The value of acceleration due to gravity yep, those are all true statements, right? Depends on universal gravity constant, depends on the mass of the Earth, different on different planets, also depends on the radius of the Earth. Oh, okay, there, all the above, all true statements. The gravity field strength at the center of the Earth. Yeah, 0, right? Because everything cancels out. We went through that story at the beginning of class, put the graph together. Yeah. So
It all cancels right at the center of the Earth. All right, carrying the lead, got Evan, Liam, Cole, Capri, top 5. If the sun were to collapse to form a black hole, okay, guys, this is about orbital mechanics. Does the mass stay the same? Mass stays the same. Distance stays the same. Tangential speed stays the same. Oh, right, yeah. How about guys got that? Right, so, yeah, conservation of mass. If the star collapses into a black hole, its mass stays the same, right? If there's any planets orbiting it, well, their distance that doesn't change. Their orbital speed doesn't change. Like from an orbital mechanics point of view, nothing changes. So yeah, it's just going to keep on orbiting just like it does, right? Yeah, the only change would be it becomes very dark. That's all. Liam on fire, moving up. Terry still top spot. When a star collapses to form a black hole, should ask this question first. To its mass. Yeah, stays the same, right? Conservation of mass, right? Now its density goes up, right? Some other weird things happen, but yeah, mass is conserved. Oh, for tidal forces to be significant, there must be a large distance where? Yeah, opposite sides of the body experiencing tides. So whatever has the tides on it, in this, like the Earth has tides, okay? You care about like the diameter of that object, the diameter of the Earth, okay? And say how far proportionally is the moon compared to the sun, right? So it's not the blue one. The blue one says you want the object causing tides to be very far away. That's the opposite of what you want, right? Whoever's causing the tides, if you want more effective tides, you actually want it to be relatively close. You just want the proportional distances from close sides to the opposite side to be a big proportion. All right. If the radius of the Earth were half of what it is now and the mass were the same, ooh. Okay. A couple of you guys got that? All right. This was a little tricky, but yeah, your the gravity field would actually go up by a factor of 4. Okay, let me show it to you guys. Okay. So start from this. If you divide out the mass of the mass of some object, you can get the gravity field of the planet, which is this. Okay. All right. Let's call it like the original gravity, and then the new gravity. So gravity constant same, mass of the planet same, because we're like packing this planet down. Okay. Got half the original radius being squared. Because what is a factor of 1/2 squared? Is that 1/4? What is 1 divided by a fourth? Is that 4 times? So 4 times gm on r squared. Okay. Where gm on r squared was the original gravity field. Okay. So the 4 times the original. Now, since Earth gravity is a shade less than 10 meters per second squared, see 10 times 4 is 40, shade less than 40, there you go. 9.8 times 4, basically, right? All right, it's the green one. Are we doing? All right. A circle is a special case of an ellipse. Yeah, you guys remember making those ellipses? Take the 2 focal points, put them on top of each other. Right? Yeah, circle is a special case of an ellipse. An object placed geometrically halfway between the Earth and the Moon. That object will fall toward the toward the Earth, right? There is an L1 point between the Earth and the Moon, but it's closer to the Moon. So yeah, geometrically halfway, you guys are right. We'll fall towards the Earth because the Earth is more massive. The early bird communication satellite hovers over the same point on Earth's equator indefinitely.
Because why? Yeah, its orbital period is 24 hours. All right, guys nailed it. To the podium with the bronze, Carrie. With the silver, Evan. And the gold, Liam. Hey, nice job, guys. Here, runners up, Cole and Capri. All right. That takes us right to end of class. All right, you guys have a great rest of your day.
Yeah, so I wasn't